My name is Darla Moore, and I'm going to be group leading for the bomb calorimeter, which we will hopefully be doing next week. So the objective of it is we want to become more familiar with bomb calorimeters. These are essential when we try to find the heat capacity properties of various substances, whether it's a solid or a liquid. Another thing is we want to find the gross heat of combustion of these substances. So we're going to be looking at various substances which we will put in the bomb calorimeter, and then we will find the change in the temperature based on it. So the theory behind it is we're going to be looking at the first law of thermodynamics, mostly the first equation where we can rearrange it in order to find what we're looking for. If we set the system to be the everything but the fuel, and we have a known fuel, we can use the middle equation where we can set the thermal capacitance of the system equal to the heat divided by the change in temperature. And then we can also rearrange if we do not know the fuel to get the bottom equation below. So this is the setup for it. On the right-hand side, it's mostly set up with 7 things. We have the igniter, the bomb, where the computer is connected, the analog to digital converter, the water bucket itself, the thermocouple, and the water stirrer. The main essence of this is going to be the bomb on the left-hand side of the screen, which has the input check valve, the pressure release valve, the electrode terminals, the crucible where we will put the fuel, the electrodes themselves, and the ignition wire. So essentially what's going to happen is that to begin the experiment, we'll put the fuel in the crucible in the bomb, and then we will add water around it. And essentially what we're doing is we're going to ignite the fuel in order to determine the change in temperature of the water, and then this will give us a rough estimate of the units of heat liberated during this. So essentially what's going to happen is we put the fuel in, we add the water around it, the electrodes in the ignition wire are going to ignite the fuel, but before we can do all that, we have to properly seal it. Inside the lid of the bomb calorimeter is a thermocouple, which will be connected to the computer, which is how we'll determine the change in temperature, which we've done in many of the experiments. Also attached to the lid is a stirrer, and what this will do is it'll rotate the water and keep it moving so that the temperature distribution is even and constant. Thus we can get a better reading and eliminate errors from that. And before we begin, we have to consider a few things. We do have to pressurize the bomb. So we're going to connect a oxygen hose to the system, pump oxygen in. We do not want to over-pressurize the bomb. That's why there is the pressure release valve. If we over-pressurize, we can get misconceived data, and it also could potentially damage the bomb calorimeter. So we're going to also have to think about how the change in temperature affects the change in pressure. We know as temperature increases, this affects the pressure. So when we pressurize the bomb, we really have to consider these things. Another thing we need to consider is the initial conditions. When we put the water in, it can't be too hot or too cold. We're going to need it to be room temperature. If it's too cold, the air around will try to warm it up. So not only will we be looking at the heat transfer from the fuel, but we will also be looking at heat transfer from the air. And then we can't use hot water because heat transfer will transfer potentially from the water to the fuel and misconceive the data. So ideally, we're going to use room temperature water. So in order to better understand the experiment, we had to do example calculations. For this one, we had 2 kilograms of water and 3 kilograms of stainless steel. So we had to go to the back of the thermodynamic textbooks and get the thermodynamic properties, which you can see with the specific heat energy values under the masses. So what you're going to do is you multiply those respectively, and then you add them together to get the total system's heat generation. The main thing we're going to look at in this experiment is the change in temperature of the system, and that's how we're going to determine how many units of heat were liberated. So we're going to go again to the back thermodynamic textbook, get those specific values and such. For this one, in the lab, we are going to be doing something that we do not know. the actual substance, so we can't really go back to the thermodynamic textbooks for that one. So we are going to be using the unknown fuel equation on the second slide. But for this one, we were able to find the change in temperature based on those tabulated values. For this lab, there are a lot of uncertainties. We have to take into account that, I don't know about y'all, but I've never used a bomb calorimeter. So there are the uncertainties of operating it, especially when you don't know if something is going wrong, if what you're doing is right. So you really have to take your time and figure out the errors that could result from it. Another thing is computer errors. I know in previous experiments we've talked about thermocouples. If it's too close to the edge, it could read a higher temperature than it actually is. If it's too far, it could be different. Thankfully, we have the water stir motor, which will kind of help alleviate these errors, so that we don't have to worry about the thermocouple as much. But we do have to worry about the analog to digital converter, which does take into account the one least significant digit. And then another thing is system errors. We aren't told when it was last calibrated, last checked, or anything as such. So we do have to consider that when we're working with this. And these are all things that we can take into account when we get the data and we can see that it's skewed or not.